Looking at the calculations required for our refraction experiment, we can see that when looking at the law of refraction, we have equation number 1 here. And in our experiment, our N1 is air and our N2 is our block. So we are going to say N1 is air, which is 1.00, and we can take that to be a constant with no uncertainty. So what we want to do is rearrange this equation in order to solve for N2, which is the index of refraction of the block. So I'm just going to refer to it as N from now on, and that is going to give us N air times sine theta 1 divided by sine of theta 2. Now we can further simplify this because we know that N air is equal to 1, so this just simply gives us sine theta 1 divided by sine theta 2. So in your experiment, you're going to use the measurements of the angle of incidence, so that will be theta 1, and the angle of refraction, theta 2, to calculate your value of the index of refraction. Now, you'll also need to propagate the uncertainty. So we have n is a function of theta 1 and of theta 2. So using our calculus form of the uncertainty propagation, that gives us delta n is equal to partial derivative of n with respect to the first variable, which is theta 1, squared times uncertainty of the first variable, theta 1 squared, times, plus the partial derivative of n with respect to the second variable, which is theta 2 squared, times uncertainty of theta 2 squared, and there are only two variables, so those are all of our terms. And this entire expression is square rooted. So the uncertainties of your thetas come from the measurements, but these values must be in radians in order to calculate this uncertainty correctly. So in your calculations somewhere, you'll need to convert the uncertainties from degrees that you measured using the protractor into radians. So the other element we need in order to propagate the uncertainty is to figure out what these two partial derivatives are. So if we start with a partial derivative of n with respect to theta 1, then we are taking the partial derivative, so di by di theta 1 of sine theta 1 divided by sine of theta 2. So because this is a partial derivative, then theta 2 is a constant. So we can actually pull this out of our derivative. So this is equal to the same thing as 1 over sine theta 2 times partial derivative di by di theta 1 of sine theta 1. And so the derivative of sine theta is cos theta. So this gives us a result of cos theta 1 divided by sine of theta 2. So that would go here in our uncertainty propagation. The second one is a little bit trickier, but we can still work it out. So the second partial derivative is di n by di theta 2. So again, the other variable, which is a constant in this case, that's going to be theta 1, we can pull that outside of our expression. So I'm going to write sine theta 1 out in front times partial derivative, so di by di theta 2 of 1 over sine of theta 2. And now there are different ways you can approach this. The way that I like to approach it is to write 1 over sine theta as sine to the power of -1. So that gives us sine theta 1 times di by di theta 2 of sine theta 2 to the power of -1. So note that this is just saying that it is to the power of -1, so it's 1 over sine theta. It is not the inverse sine function. That gives you a different calculation. So make sure that you are not confusing the two. So now at this point, we can use the chain rule to take this derivative. So I have my constant in front, sine theta 1, and the chain rule says we take the derivative of the outer function, so that would be -1, and then the inside stays the same. And then this derivative is to the power, now gives us to the power of -2. And then we take the derivative of the inner function. So times the derivative of the inner function, which would just be cos of theta 2. So if we combine this all together, we end up with negative cos theta 2 times our sine theta 1, which was our constant that just stayed out in front the whole time. And then that is going to be divided by sine of theta 2 squared. So this is our second partial derivative, which belongs in this part of the expression here. So now we have worked out how to determine our partial derivatives and how to propagate the uncertainty for the law of refraction calculations. Looking at equation number 2, the equation relating the index of refraction to the critical angle, we can do a similar type of operation as we did with equation number 1. So first we want to solve. So we have n is equal to 1 over sine of theta c. And now we have n is a function of theta c. So the uncertainty of n using the calculus method is partial derivative of n with respect to the first variable, so that's theta c squared times uncertainty of theta c squared. And there's only one variable in this case, so that is our only term. Now everything under the square root is also squared, so we can cancel a couple of things out. So that gives us absolute value of this partial derivative times uncertainty of theta c. And again, the uncertainty value here has to be in radians in order to calculate the correct result. So to take this partial derivative, we can use the same method as before. So I'm going to write di by di theta c of sine theta c to the power of -1 and apply the chain rule. So we have derivative of the outer function, so we have -1, inner function stays the same, to the power of -2, and then we times it by the derivative of the inner function, which is just cos of theta c. So that gives us negative cos theta c over sine theta c squared. And now this is what goes into our partial derivative part of the expression, and it is just plus or minus absolute value of that times theta c. Finally, for the last part of the experiment, we want to verify equation number 5. And what we did is we set up the experiment so that we can calculate both sides of this equation. And we want to verify whether or not the left side equals the right side. So to simplify things, I'm just going to say let x equal d over w, and then we can say y is equal to sine of a over cos of theta r. So we need to propagate the uncertainty for both sides, meaning we need to find the propagation of uncertainty for x and for y. So x is a function of both d and w. That means we want to set up our expression for delta x as partial derivative of x with respect to d squared times uncertainty of d squared plus partial derivative of d with respect to w squared times delta w squared. And that would be square rooted. And then y is a function of theta a and theta r. So those were your two measured quantities for the right side of the equation. So we are going to use the calculus method to set up our expression for delta y. That's going to be partial derivative of y with respect to the first variable. So that's theta a squared times uncertainty of theta a squared plus partial derivative of the second variable. So partial derivative of y with respect to theta r squared times delta theta r squared. And once again, the angles and their uncertainties all need to be in radians in order to get the correct result here. So I'm going to leave it here. In order to complete these two expressions, you'll need to determine these partial derivatives so that you can calculate the uncertainties of both the left and the right side of equation number 5. And you want to compare the result for the left side and the right side to see whether or not the values agree within uncertainty.